Okay, in this video, I want to talk about writing the equation of planes in space. And we're going to come with both a vector form of the plane and a Cartesian form of the plane. We can even do parametric. So we'll talk through that. There is a video of me teaching this 3 years ago, maybe. So you only see me, but you can hear the other students in the class. I'm making another video because that one's 34 minutes long. And so the goal was to give you a chance to get this figured out without taking 34 minutes. But the advantage of that is that you can see all of me and you can see how I'm modeling things. And if this video isn't sufficient, then go watch the other one because I think it would be helpful. Okay, so the first thing we want to talk about is when we discussed the equation of a line. If you remember, if we had a line in space, the first thing we would do is we would use a direction vector. I lied. We would use a position vector to get you from the origin, so say this is the origin, to some particular spot on the vector, on the line. Okay, here we go. So we've got to get a position vector so that we're somewhere on the correct line, and then we can use a direction vector that moves up and down that line. Okay, so say this is the point O and this is the point A, and somewhere out here is the point B. What we would have done is we'd have said, okay, well x, y, z is equal to the vector OA plus some parameters, so say t or lambda or whatever times the vector AB. What that enables us to do is that says, okay, I'm on the line, and now I can travel up and down the line. Well, what we're going to do is we're going to use this idea to start talking about the equation of a plane. Except a plane, now what we have is, say this is our plane, and here's the origin somewhere. What we have to do first is we have to get to a point on the plane. Okay, so say this is the point A. Then we're going to first need to get from the origin to that plane. And then if I have one direction going, say, this way, and here's the point B, this would, if I multiply that by any scalar, that allows me to move up and down that particular line. But let's say I want to get somewhere over here. Well, what I would need is I would need another vector on the plane. Okay, so say there's the point C. I would need another vector on the plane as long as it's not parallel to the first one. Because what we're going to do is we're going to get to the plane, we're going to travel in one direction, and then we're going to turn and travel in a different direction. I like to think of, I put a link in your distance learning stuff of the little video from Toy Story of the claw. Okay, so what you have to do is as you're using that claw to get a toy, you go a certain direction this way, and then you can go a certain direction here, and then you can drop down and pick up the toy in theory. So the way that this works, so that's what we're doing. We want to be able to get to any point. So if I multiply this vector by a scalar and this vector by a different scalar, that'll enable me to travel anywhere up and down this and then turn it and go a different direction. Okay, so initially we have our OA, so we have to get to the plane. And then we have one parameter times that vector AB. And then we have a second parameter, so lambda and mu are often what we use. They don't have to be, times the vector BC. But I want to make sure that I have the opportunity to put in different values. Okay, so like if AB is this long and BC is this long, say I want to go twice AB, so here, and then say that's the other one. I don't necessarily want to go twice BC. I might want to go in a negative direction or something like that. If this is hard to see with me trying to keep it on a piece of paper, go watch that other video. So hopefully that will be helpful. So this is how we would write the equation. This is the vector form of the equation of a plane. Okay, so we have a position vector, so we've got to find a spot on the plane, and then we have two direction vectors on the plane as long as they're not parallel to each other. The other thing we want to talk about is that when I have a plane, so say I've got vector, here's A, here's B, and then I've got somewhere down here is point C. If I want to make sure that I've got, what we're going to need is we're going to need to find something that's normal to the plane. Okay, a normal vector is something as a vector let me make this part dotted, is a vector that's perpendicular to my plane. Okay, so sometimes we refer to that as the normal vector. Well, sometimes, often, we refer to that as the normal vector. We can say that it's perpendicular to the plane, we can say that it's orthogonal to the plane, and it's the normal vector. So all of those things mean the same thing. So if you think about it, the normal vector dotted with vector AB, if vector AB is on this plane, if they're perpendicular, that had better equal 0. Or the normal vector dotted with vector BC had also better be 0. Well, so if I know that if I have these 3 points, say I have point A, point B, point C, which will be my example in just a second. If I have those 3 points and I want to find a normal vector, what I can do is I can take vector AB and cross it with vector BC, and that will find something, it will be parallel to the normal vector. Now, the normal vector can be any length, and often we kind of reduce that as necessary. But anyway, so the whole point of that, let's say my normal vector is the vector, oh, that's funny. That's the pre-count notation. My bad. Okay, say it's the vector n1, n2, n3. Actually, let me do it this way. Let's say that the normal vector is the vector a, b, c. Okay, what we're going to find is that I can come up with a Cartesian form of the plane, where I take the Cartesian form of the plane will be ax plus by plus cz is equal to d. And what's going to happen is if I plug in, these are going to be actual numbers, a, b, and c, based on the normal vector. And then I'm going to plug in a random point on the plane. I'm going to show you in the example. It's going to make more sense. But then I will evaluate and figure out this d value, and this becomes the Cartesian form of the plane. And you'll notice, so if I have something like, well, 3x minus 2y plus z equals 11, the normal vector would be the vector 3, negative 2, 1. That's going to be normal to this plane. You'll notice that this is something that we would have seen when we were solving systems of 3 variable equations. And so it all comes together. Okay, let me not get ahead of myself. So here we go. They say find the equation of the plane through those 3 points. And if we want the vector form, what we need to do, there's many answers, okay? The vector equation of a plane or of a line, there's not necessarily one unique answer. When we get to the Cartesian, we can reduce this, and so there is kind of a best answer, but not with a vector. Okay, so this plane is going to be x, y, z is equal to, I want a position vector, so I might as well take vector OA, and that's negative 1, 2, 0, plus I need a variable, so say lambda, and I'm going to do vector AB, so 3 minus negative 1 is 4, 1 minus 2 is negative 1, 1 minus 0 is 1, and then I need a different variable, so say mu, and then I'm going to do vector BC. Okay, 1 minus 3 is negative 2, 0 minus 1 is negative 1, 3 minus 1 is 2. Hopefully I know how to add and subtract. But this is a vector form of an equation of a plane. And so you can change that to parametric if you feel so inspired. Just x is equal to negative 1 plus 4 lambda minus 2 mu. Y is equal to 2 minus lambda minus mu. And z is equal to, well, it would just be lambda plus 2 mu. Okay, that behaved just like we saw with the equation of lines. Okay, so now if we want to come up with a Cartesian, what we need to do first is we need to cross. Now, keep in mind, this vector is not on my plane. This was the vector that got me from the origin to a point on the plane. Okay, these two are vectors that are actually on my plane. So if I want to find the normal vector to the plane, I have to use these two direction vectors that are actually in the plane. And so this is I, j, k. 4, negative 1, 1, negative 2, negative 1, 2. There is a way, and the formula book talks about it, and you multiply different things and subtract. I never can remember that. So I'm always back here. That's a negative 1, that's a 1, that's a negative 1, 2. Okay, obviously this should not be the very first video you watch because we've done a bunch to lead up to this point, right? 4, negative 1, negative 2, negative 1. Okay, So here's hoping I know how to add, subtract, and multiply. -2 minus -1 means a plus, so this is negative I. This is 8 minus a -2 is +2, so, and then there's a minus 10j. -4 minus 2 is -6k. Okay, so what we have here is that the normal vector to this plane is the vector -1, -10, -6. What we can do here is that we know that the normal vector is k times any of that. Well, so let's just use the vector 1, 10, 6 so that we don't have as many negatives to deal with. Okay, so what we're going to do is we're going to say, okay, well, this is our ABC, so we want AX plus BY plus CZ is equal to D. So I have X plus 10Y plus 6Z is equal to some value D. And now at this point, I'm going to plug in one of the points that I know. I'm actually going to plug in two of them just so that you can see it wouldn't matter. So I'm going to use this -1, 2, 0, -1, 2, 0 equals D. Oh, you couldn't see what I was doing. I'm so sorry. Okay, so what this gives me here is -1 plus 20 plus 0. This D value is equal to 19. Okay, let's say I used a different point. Let's say I used this one. Say I have, what was it? It was X plus 10Y plus 6Z equals D. Let's plug in 3, 1, 1. 3 plus 10 times 1 plus 6 times 1 equals D. We just said a minute ago that D was equal, there it is, to 19. What happens here? 3 plus 10 plus 6, 9 plus 10 is 19 is equal to D. Okay, so the Cartesian form of this plane, the final answer is X plus, can you see what I'm doing? 10Y plus 6Z is equal to 19. And that is the Cartesian form of the equation of the plane. You'll notice I could multiply through by 2. I could multiply through by -1 or whatever I want to do. But in order, if it's reduced as possible, there's really one best answer for the Cartesian form. The vector form, not so much. Okay, so what I had done, remember, was this was vector OA plus lambda times vector AB plus mu times vector, what was that? I used BC, I'm pretty sure. But I could have said OC, and then vector CA, and vector BA, or whatever I wanted to do. I had choices on this. So this one is a little, I mean, it's helpful, it's important, but it's not quite so, given the same 3 points, we may not all come up with the same equation, but we should all come up with the same Cartesian form. Okay, hopefully that was helpful. Let me know if you have questions. You'll definitely want to practice. And go watch that longer video if you want to see me in the classroom, if you missed that. But it was a few years ago, but it's still good. All right, enjoy.